Thank you, and thanks to everyone for coming, and thanks to the organising committee for giving me the opportunity to speak. So I'm Niall. I'm a Mansfield Fellow at the University of Nottingham in physics, but I'm also one of the co-founders at Circle Magnetics Limited. So I'm going to talk about something called the signal space separation method. And obviously, with the sort of WOPM audience, I'm going to introduce that to people who aren't familiar with it. I'll then talk about how, in trying to apply this method that's been developed mainly for cryogenic MEG to OPM-MEG, there are certain challenges and the sort of steps we've taken to overcome them. I'll show an application of this method and how it can really help us to record good quality data in quite noisy environments, such as in lightweight shielded rooms. And then I'll talk about how we can improve it by looking at system calibration. So to think about SSS, or the signal space separation method, we first think about Peter, sit down. That was brave of me. So we think about MEG, we tend to have an array of magnetometers, whether they be squids or they be OPMs, that are arranged in some sort of helmet. And we place those sensors inside a shielded room. And what we're generally most interested in is the signals that come from the brain. So we put the head inside the array of sensors so that the brain is inside this array. We also have many other signals that we detect. So passing vehicles and traffic can cause interference signals that we still measure despite the shielded room. We have, metro light rail systems. We have tramways in Nottingham. There's trams here in Sydney, things that pass by that generate artifacts. Also, any general mains electricity generates artifacts, and things like air conditioning units can generate artifacts that can creep into our data. These tend to be outside the shielded room and outside the helmet. More importantly, there are also, of course, other biomagnetic signals, such as the heart and muscles, that can generate signals that we're not interested in, that aren't coming from the brain. So we can sort of separate these into sources that are internal to the helmet, so the brain is inside the helmet, the array of MEG sensors, and external sources. So some of those are inside the shielded room, some of those are outside the shielded room, but they are all in general outside of the helmet. So Sami Taulu and colleagues developed in sort of 2005 a method called signal space separation to model the data we collect from a multi-channel MEG system using spherical harmonics. So this first term here that varies with 1 over r to the power of the harmonic order, they best describe sources of field that diverge at the origin. So those are best describing sources that are closer to the sensors, closer to the origin of your system, which is like the center of mass of your sensor array, than the sensors themselves. The second term, which are more regular harmonics, so homogeneous fields, field gradients, etc., they diverge at infinity, and they therefore best describe sources that are further away from the origin than the sensors themselves. So you can sort of split these two into a term of spherical harmonics that model the internal sources, and a term of spherical harmonics that model the external sources. And the only thing we need to make sure is that we have enough channels in our system such that we can accurately determine what all of these vectors look like. So what we do in the traditional application is cast this as a matrix equation. So we have some matrix S, which is our signal vectors, some weights X, and we try and map those vectors with these weights to the data that we collect, which is this phi. So we can separate this into internal vectors and external vectors, and we can do the same thing with internal and external weights. We know what the data is. There's phi from our data that we collected. We know what this S matrix is because we know our system geometry. We know the position and orientation of each sensor. And then we can estimate weights just by doing the pseudo inverse of this S matrix. And then we can estimate separately two sets of signals, one signal that just comes from the internal sources that we're interested in, and one that comes from the external sources that we're not interested in, and we can throw away and leave ourselves with some nice data without artifacts. So that's the conventional MEG application. That works with about 300 channels. Most OPM-MEG systems we get in there, but at the moment the typical level is somewhere between 100 and 200 channels, maybe a little bit more. So the array needs to maximally distinguish between what is an internal source, what is an external source. And this is quantified by the angle between these internal vectors and those external vectors. It looks a little something like this. So if our data is somewhere up here, Our external vectors probably describes most of the data. Most of the interference is bigger than the noise signal. And then we have this angle between the internal signal there. So this angle is not 90 degrees. But for example, in a sort of cryogenic MEG system, the mean angle between all of these vectors is around 10 degrees. So it's not a lot. If we use multi-axis OPMs, that angle increases significantly. So, we can get with this is the sort of 192 circa system that has a subspace angle of about 64 degrees. So just multi-axis sensing, which we've seen before in other areas, multi-axis sensing should give us a real big advantage in SSS for OPM. However, this low channel count comes back to bite us. So, compared to the number of basis vectors, we've only got like between 100 and 200 channels. What we worked with Samu on was to exploit this S matrix and try and balance out our reconstruction. So if we have too few channels, actually what happens is you get something called noise amplification. So what we do is we take each column of the S matrix, and rather than inverting it, we extract a few columns and say that these lower order harmonics will always describe more signal energy than the higher order harmonics. So let's do a small pseudo inverse of a small amount of those, subtract that from our data, and then go back and do the higher order harmonics as we go. So this iterative solution can really help us stabilize the noise. So this graph here shows the increase in noise. So this factor is basically what you'd multiply your noise by if you were doing SSS. So that, numbers of 100, you get quite a lot more noise. And actually, you can see that as we increase the complexity of our model, this noise amplification goes up and up and up. With OPMs, we're closer to the head. We want to be increasing the complexity of our model. We want to be measuring higher spatial frequencies to get higher spatial resolution, but actually it's difficult. If we incorporate this iterative inversion method, you see we massively reduce that noise amplification factor. So there are ways of stabilizing SSS to apply it to OPM data, but we do have to just be careful not to amplify noise when we do. So let's look at some real data. So we've got single channel, so with single tracking, and then here's our blue is the raw signal of one OPM from a 192 channel system that is measuring interference generated by an external coil system. So this is controlled interference that we're generating using one of our nulling coils just to make an extra weird signal. If we apply SSS, because this is an empty helmet, we should get no internal signal left over. So if we apply SSS and look at our estimate of the internal signal, we should just see a nice flat line. So you see what in red, now we can see the SSS reconstructed signal. It's not quite a flat line. If we compute the shielding factor, though we get a shielding factor of about a factor of 9. So it's pretty good, but it's not, there's still a strong signature of that external interference in our data that we don't necessarily want. If we zoom in, we've still got about a 20 picotesla level artifact there that we don't really necessarily want. So why might that be? If you talk about some of the limitations of SSS in general, the quality of the reconstruction is affected by two key things. One of them is the truncation order, so that's how many channels and how many vectors we put in our model. If we don't have enough vectors and we can't quantify everything, we get mixing of signals across different vectors to account for it. It's also really crucial that we have accurate system calibration. So what we mean by system calibration in MEG, of course, is the channel position, the channel orientation, and the channel gain. We need to know those really well in order to make sure that our data are modeled properly. And each of these errors results in mixing across the inner and outer subspaces. So another method that was developed for cryogenic MEG was called spatially temporally extended SSS. And it considers the strength and the temporal profile of the interference signals versus the brain signals. So this, for example, might be a sort of 50 hertz or 60 hertz power line artifact that is going to be fairly continuous throughout an experiment. It's not really going to change in amplitude, and it's going to sort of be correlated nicely across all sensors. If we think about a brain signal, that might be more short and punctate, so you might not, it will be smaller amplitude. It might not necessarily correlate as well across sensors and across time. So what we can do is look at the intersection of the two subspaces, the two signals that we reconstructed, and say actually anything that's correlated over a reasonable length up to a certain level is unlikely to be brain activity, and we can project it out of our data. So this is referred to as TSSS. And you see now, if we add the yellow TSSS signal to our example data, you see that's now much flatter. And if we look at the shielding factor, that ratio is now about 250, so doing a much better shielding and really rejecting the stuff in our data that we don't want. And again, if we zoom in, you can see that 20 picotesla has been massively reduced to something that's basically sort of artifact free at a certain level. I just want to flag up another method to do this. So me and Sammy developed this iterative stabilization of the SSS matrix. Tim Tierney at UCL has developed something called the adaptive multipole model. That's published in Human Brain Mapping earlier this year. This is a similar multipole modeling method, except Tim used a different geometry, he used spheroidal geometry, and he used a projection that's orthogonal to the external space to deal with noise amplification. So it's slightly different, but trying to achieve the same goal. So that's SSS, that's TSSS. I'm now going to show you some example applications that we've been working on. And the first one is trying to do OPM-MEG in a lightweight shielded room. So shielded rooms in general are very, very important for MEG. They're almost more important for OPMs, where we need to provide zero background field environments for surf operation. But they tend to be very expensive, they tend to be very heavy, and they're really difficult to site. You have to have, you have to basically put them in a basement, and you need a lot of room. If we could start to deploy MEG and take advantage of the sort of cryogen-free nature of OPMs, if we could start to deploy these systems in lighter, cheaper, easier to site MSRs, that would be really useful for dissemination of the technology. We were building a new MSR in Nottingham, and we paused the construction when it only had one layer of mu metal and one. So it looks something like this. There's a little bit of the outer mu, but it's not a complete shell, and you can kind of see the copper and then the inner mu metal. And then there's this wooden structure here is just a triaxial Helmholtz coil to back off the remaining field. If we compare the noise in our two rooms in Nottingham, so in blue, this is in a 5-layer MSR, so that's 4 layers of mu metal and 1 layer of copper. We get a really nice noise floor. And if we did the same thing in this light MSR, we get around an order of magnitude increase in the noise, so a lot more noise. If we apply TSSS to this empty room data, though, what you see in the yellow is that we can bring the signal from the red all the way down in the empty room level to be similar to the 5-layer room. So TSSS is working really well at plowing through all this interference, taking it out, and giving us back some MEG data that has a noise floor low enough for us to hopefully see neurological signals. We tried this first with a phantom. So we have a sort of a triangular dry phantom, so it generates a sort of current dipole measurement. We drove it at about 13 hertz to simulate a sort of evoke response experiment and averaged over a lot of trials. And this is our results in our 5-layer room. So regardless of what we do, if we filter the data, we see the nice signal. If we do SSS, we see the nice signal. We're not distorting the temporal form of the signal. And if we do TSSS again, we see the nice signal. If we do that in our light room, though, you see in the first plot, just averaging and filtering doesn't really give us back the information we need. SSS starts to pick it out, but there's some issues possibly with various things, and TSSS leaves us back with the sort of beautiful, reconstructed data that we expected to see. If we look at the single trials on the TSSS data, they're sort of, they're less than 1,000 femtotesla, but applying TSSS to data in this lightweight shielded room, we can recover the nice signal. We then did this on MEG, so we did a right-hand finger abduction. And again, if we look at our raw data, what we'd expect to see here is a sort of blue region where we have a decrease in beta power during the finger movement, and we don't really see it just in the raw data. If we do a beamformer, which is a source localization method, it localizes broadly to the correct side of the head, but what it doesn't show us really is spatially specific detail. If we do this in our TSSS data, it pulls out that nice beta response, and you can see it sort of focuses in the spatial specificity of the beamformed image. So we know better spatial precision of where it's coming from. And we can quantify this just looking at the fall off of the shared variance of the electrical activity in different voxels, and you see that it's much sharper if we apply TSSS compared to just doing the filter. So the final thing I'm going to very quickly talk about is system calibration. So improving the array calibration should improve SSS. We'll know more about our signal. And we use the method that Jonas developed with Peter at Sandia to use the electromagnetic coils that are used for nulling to actually generate known fields for calibration. And there's actually a talk a little bit more on this at BioMag that actually Tyler from Circa is giving on using these nulling coils for calibration, as well as the halo that QSpin has developed. So more information at BioMag on that. But just looking at the effects on SSS, if we use the assumed calibration, we already saw we had about 20 picotesla. If we use our coil guided calibration, it does a much better job. So we're getting, around a 10 times improvement in calibration. And I'll just skip that, but TSSS still helps. So we're still at some level of, where we need to do something else, maybe improve the channel count and improve other things. So just to summarize, multiple modeling methods can be used with OPM-MEG technology. In well-shielded environments, TSSS doesn't do a lot, but in high noise environments, it's really important before you do your beamformer. What we're currently doing is building just a truly single mu metal layer room, and we're going to see how far we can get with that. So thank you all for listening, and happy to take any questions.